Hello students, in the last lecture we have studied about capacitor and type of capacitor. Along with that we studied the grouping of capacitor. The basic function of a capacitor is to store energy. Now in this lecture we are going to study how the energy is stored in the capacitor or how we can find out the energy stored in the capacitor. As you can see in the diagram, there is a parallel plate capacitor which is basically uncharged. It is connected across a battery of potential V and the switch is open. Since the switch is open, no current flows or no charge transfer takes place. Hence, the potential between the two plates of the capacitor will be zero. Moving on, let's say after some time, since the switch is being closed, electron starts flowing. And once the electron starts flowing, the two plates gets charged up. The plate on the right hand side get minus Q charge, whereas the plate on the right side get plus Q charge. Since the charges have arrived or arised on the two plates, there will be a potential difference across the two plates which is given by V dash. This is a partially charged condition. Once the parallel plates are fully charged, the parallel plate capacitors are fully charged, minus capital Q will arise on the right plate, whereas plus capital Q will arise on the left plate. Since it is fully charged, means there will be no further transfer of charge. In that case, the potential across the parallel plate capacitor will be equal to the potential of the battery which is given by V. Now coming to this diagram. Once the right plate of the parallel plate capacitor was charged by minus Q, it transferred some of its charge to the left plate. Let's say it transferred some of its charge to the left plate, and that charge transfer is given by dq. Since the charge is transferred from the right plate to the left plate and that charge is given by dq, then some amount of work has to be done in transferring this charge. Once some amount of work is done in transferring this charge, that work done will be stored in the capacitor in the form of energy. So the work done in moving dq charge from negative plate to positive plate of the capacitor, here as I have already told you, we have assumed that a small charge, that is dq, is being transferred from the negative plate to the positive plate. So the work done will be given by, as we know, work done given by Q into V. Here the charge transfer is dq. So dw will be equal to dq dot V dash. V dash is the potential between the positive and the negative plate of a parallel plate capacitor. So now potential difference is given by V dash is equal to Q by C. We have already discussed the capacitance of a electrical capacitor, and from that we get V dash is equal to Q by C. Putting this, we get dw is equal to Q by C dot dq. dq is the charge transferred. Now we need to find out total work done in charging or fully charging the capacitor. So initially when the capacitor was uncharged, the charge on each plate was 0, and once it was fully charged, the charge became capital Q. So we'll integrate dw from 0 to capital Q. Putting the value of dw, that is Q upon C dot dq, integrating it from 0 to capital Q, we get Q square, capital Q square upon 2C. So this is the total work done in charging the capacitor from uncharged to fully charged. So this will be the work done. Now as we know that electric forces are conservative on nature, thus this work done will be stored in the form of potential energy. So the work done, that was capital Q square upon 2C, becomes the potential energy or the energy that is being stored in the capacitor while charging it. So the formula of potential difference becomes Q square upon 2C. Now we know that Q is equal to CV. So we put the value of Q over here, we get half V square, and similarly we'll get half QV. So these are the three formulas using which you can find out the energy stored in the capacitor. Moving on, now we'll find out energy density of a parallel plate capacitor. Energy density is defined as the total energy stored per unit volume of the capacitor, which is given by small u. So small u is equal to total energy upon volume. As we have already discussed, total energy given by half CV square upon AD. Now we know that the capacitance of a parallel plate capacitor is given by epsilon naught A upon D, where A is the area of the plate, D is the distance between the two plates, and potential is given by E into D. Putting this in this equation, we finally get small u is equal to half epsilon naught E square. This is the formula for finding out energy density of a parallel plate capacitor. Next we are going to study is common potential. Now what basically common potential is? Let's say there are two charges which are being separately charged. And now if we connect those two charges with a wire, then the charge will flow from a higher concentration to the lower concentration. This process will continue until the charge or the potential of both the capacitor becomes equal. We know that there is a charge transfer only when there is a potential difference. If the charge, two capacitors have different potential, there will be a charge transfer, and it will stop once both the capacitors attain a same potential, and that same potential is known as common potential. So when two charged capacitors at different potential are connected by a conducting wire, charge flow from the one at higher potential to the one at the lower potential. This flow of charge continues till their potential become equal, and this equal potential is known as common potential. Now how to find out that? Let's say C1 is the capacitance of the first capacitor, C2 is the capacitance of second capacitor, V1 is the potential of first capacitor, whereas V2 is the potential of second capacitor. For finding out common potential, we would be using the conservation of charge. So the total charge before conservation will add up charge of each capacitor, and we know that charge Q is given by CV. So for the first capacitor it will be C1 V1, and whereas for the second capacitor it will be C2 V2. After they have attained a common potential, the transfer of charge will be stopped. So total charge after sharing will be C1V, where V is a common potential, plus C2V, V is a common potential. We can write this as bracket C1 plus C2 into V. Now by conservation of charge, total charge before sharing must be equal to total charge after sharing. So we put the values, we get V, that is a common potential, is equal to C1 V1 plus C2 V2 upon C1 plus C2. Using this formula we can find out the common potential. Up till now we have studied that in the parallel plate capacitor, the gap between the two plates are filled with air or vacuum. What if it is filled with a conducting slab? Now what will be the effect of putting a conducting slab between the two plates of a parallel plate capacitor? First let us study the diagram properly, then we'll move on. There is a parallel plate capacitor with a distance between the two plates to be D. This is the electric field which has been produced inside the capacitor, which is given by E0. Now get a conducting slab of thickness T between the two plates. Now, as we know, inside the conducting slab the electric field is always zero. Since it is a conductor, we have already discussed in the electrostatic of conductors in the earlier lectures that the electric field inside a conductor is always zero. So you can see from a diagram that E0 is only in the distance D minus T. सिर्फ वो D minus T के अंदर रहेगा, T के अंदर there is no electric field. As we have already discussed, a conductor of thickness T which is less than D, where D is the distance between the two parallel plates of a capacitor, is introduced in the capacitor. So the uniform electric field, that is E0, which has been produced by the plates of the capacitor, will exist over a distance of D minus T. because in the region T there is a conducting slab and the electric field inside a conducting slab is 0. So the potential difference will be V is equal to E x. We know that V is equal to Ex, where x will be equal to D minus T. So we know that for a parallel plates or for a plate, electric field is given by sigma by epsilon naught. So putting this, we get V is equal to sigma by epsilon naught into D by T. Now we know that sigma is equal to Q upon A. Sigma is basically surface charge density, which is given by charge divided by area. Here A is the area of the parallel plates of the capacitor. So putting, we get V is equal to Q upon A epsilon naught into D minus T. Now as we know that capacitance of a capacitor is given by Q upon V. So putting the value over here, we get Q A epsilon naught upon Q D minus T. So I cancel out Q, I finally get A epsilon naught. If I take out D common from here, if I take D common, then I will get 1 minus T upon D. And as we know that the capacitance of a parallel plate capacitor is given by A epsilon naught D. So in place of A epsilon naught upon D, I'll write C naught. So the formula becomes C is equal to C naught upon 1 minus T upon D. It is clear from this that the capacitance of the capacitor when a conducting slab was introduced is greater than C naught, where C naught is the capacitance of the parallel plate capacitor when there was only air or vacuum between the two plates. It is always greater. What if T is equal to D? T is equal to D means we completely fill the gap between the two parallel plates with a conducting slab. If such a condition arises, then the capacitance becomes infinity. This is because we know that C is equal to C naught 1 minus T by D. If T is equal to D, we'll get C is equal to C naught 1 minus 1, and hence C will become infinity. It means if we fill a parallel plate capacitor with a conductor and we completely fill the gap, in that case the capacitance will arise or will become infinity. Now what if the parallel plate capacitor is filled with a dielectric slab? Initially we have studied that it is filled with a conducting slab. Now we'll study what will be the effects if a dielectric slab is kept in the gap between the two parallel plates of a parallel plate capacitor. So in the diagram you can see that these are the two parallel plates of a capacitor. I have kept a dielectric slab of thickness T, where D is the distance between the two parallel plates. As we know, inside the dielectric there is a weak electric field produced. Let's say it is given by EP. The electric field produced by the two plates is given by E naught. So the net electric field inside the dielectric slab will be given by E is equal to E naught minus EP. So a dielectric slab of thickness T is greater than D, is introduced. So the uniform electric field, that is E naught, produced by the plates of the parallel plate capacitor will exist over a distance D minus T. Another electric field E is equal to E naught minus EP, that is inside the dielectric slab, will be along a distance T. So the net potential difference will be the sum of these two electric fields. So I have written V is equal to E naught D minus T, that is the area which is not filled by the dielectric slab, plus ET. T is the thickness of the electric slab, and E is the electric field inside the dielectric slab. As we know, we have earlier discussed in the earlier lecture, the dielectric constant is given by E naught upon E. E naught is the electric field in vacuum, whereas E is the electric field in the dielectric slab. So E naught upon E is given by epsilon R, that is dielectric constant. In some of the books, it is also written to be K. The dielectric constant is also written as K. I have used epsilon R because K is widely used as Coulomb constant also. So to reduce confusion, I have used epsilon R. You can use K as well. It is your wish. If you wish, you can use K instead of epsilon R. So from here I get E is equal to E naught by epsilon R. If I put this in first equation, I'll get E naught d minus t plus E naught t upon epsilon R. If I take E naught common from this, I'll get E naught d minus t plus t upon epsilon R, or you can say k. Now as we know, E naught is given by sigma by epsilon naught. So putting this, I get V is equal to sigma by epsilon naught bracket d minus t plus t upon E epsilon R. Sigma, the surface charge density, is given by charge upon area. So putting this value, I finally get V is equal to Q upon A epsilon naught multiplied by d minus t plus t upon epsilon R. As we know that the capacitance of a capacitor is given by Q upon V. So putting this value, I finally get C is equal to epsilon naught d minus t into 1 minus 1 upon epsilon R. What is being done here? I have taken t common. So Q will be cancelled out. It will be A upon epsilon naught d minus t common 1 minus 1 by epsilon R. So this is the formula for finding out capacitance when a dielectric slab is being introduced. What if T is equal to D? It means the dielectric constant is completely filled in the gap between the two parallel plate capacitor. In this I'll get, instead of T, I'll write D. On solving, I'll get epsilon R, epsilon naught A upon D, and we know that epsilon naught A upon D is the capacitance of the capacitor when there was air or vacuum. Finally we get C is equal to epsilon R into C naught. It means if we introduce a dielectric slab which completely fills the gap between the two parallel plate capacitor, which has a dielectric constant K or epsilon R, then the capacitance becomes K times the capacitance of the capacitor when there was air or vacuum between the parallel plates. Moving on, what if there are more than one dielectric slab? I have taken this diagram in which they have put 4 dielectric slabs of dielectric constant ER1, epsilon R1, epsilon R2, epsilon R3, epsilon R4. You can write K1, K2, K3, K4, and the thickness of them is D1, D2, D3, D4 respectively. Now how to find out the net capacitance in this case? We know that C is given by Q upon V, Q is given by sigma into A, whereas V we have already discussed is given by sigma upon epsilon naught, D minus T plus T upon ER. You can write K over here as well. So on solving, I get sigma will be cancelled out. So I get A epsilon naught D minus T plus T upon epsilon R. If T is equal to D, this will become 0, and I'll get C is equal to A epsilon naught D by epsilon R. Now we'll use this concept and find out the capacitance by simply adding up the capacitance due to each dielectric. So what we'll write is C is equal to A epsilon naught upon, first thickness is D1 epsilon R1, so D1 upon epsilon R1 plus D2 upon epsilon R2 plus D3 upon epsilon R3 plus D4 upon epsilon R4. You can write this A epsilon naught upon D K1 D1 K1 plus D2 K2 plus D3 K3 and so on. So using this formula you can find out the capacitance if more than one dielectric slab has been introduced in the parallel plate capacitor. What if the dielectrics are filled in this manner? So in this case what we'll do is we'll consider the single parallel plate capacitors of two parallel plate capacitor which are connected in parallel combination. We'll divide it from here. यहाँ से divide कर देंगे तो ये 2 बन जाएंगे. And we'll find out the combination. In parallel combination, net C is given by C1 plus C2. Let's say the total length of the parallel plate capacitor was given by L. For the first, let's say length is L1, whereas for second, let's say length is L2. The area is A. The area was A only when the length was L. Now what will be the area if the length becomes L1, and what will be the area if the length becomes L2? So it can be found out easily. That is, for length L, area was A. So for unit length, area will be A upon L. So for length L1, area becomes A upon L into L1. Similarly for L2, area will become A upon L into L2. Now we have divided the capacitor. Now we have considered two parallel plate capacitors of capacitance C1, C2, which are being filled by a dielectric slab. The area of first capacitor is A1 into LA into L1 upon L, whereas that of second is A L2 upon L. So area of first capacitor A1 is A upon L into L1, whereas that of second capacitor is A L2 upon L. Now we will find the net capacitance by formula of parallel combination, that is C is equal to C1 plus C2. If I put it, I'll get C is equal to epsilon R1, because it is being filled by the dielectric constant epsilon R1. So epsilon R1 A1 epsilon naught upon D. As we know that C is given by epsilon naught A D into epsilon R if there is a dielectric constant. So epsilon R1 A1 epsilon naught upon D. Similarly, plus epsilon R2 A2 epsilon naught upon D. The thickness between the two parallel plate capacitor remains same. From this, if I put the value of A1, it will be equal to A L1 upon L. For A2, it will be A L2 upon L. तो अगर उनको पुट करेंगे तो दिस विल बी द इक्वेशन. इसमें से कॉमन निकालेंगे भी एप्सिलॉन नॉट A LD will get epsilon R1 L1 plus epsilon R2 L2. अगर एक और है then plus epsilon R3 L3 and so on. So using this formula you can find out the net capacitance if the electric are arranged in such a manner. Thank you students for listening patiently.